And good morning, everyone. This is our makeup session for PerfWeb 84 Day 2, when we were going to be going over integrating the CRRT circuit into the ECMO circuit, which obviously has the advantage if you have a patient already on ECMO that then goes into renal failure or some other problem where CRRT would be appropriate. You don't want to have to stick that patient. So we all understand the reason why we would want to integrate it. The question is, how do we integrate it? And how do all of those pressures interplay with each other? And this actually was asked of me. And Anil, I hope you're watching today. I'm not monitoring the YouTube or anything like that. So if you send a message over, Magic will let me know. And but hello to you in Mauritius. And this was something you had asked about, and I wanted to show you and be able to discuss it, as opposed to just sending you a diagram of this is how we do it, because there's a lot of nuance associated with when you do this. As I said, a lot of the pressures will interact with each other, and there's things you should be looking for and considering before you just plug it into your ECMO circuit. Of course, we all understand that anytime you plug a CRRT machine or anything into your ECMO circuit, it carries risk, and you have to be careful that you don't open a stopcock the wrong way on the negative side and potentially suck in a bunch of air, or open it on the positive side and have a bunch of blood loss. So taking all of those things into consideration, the final thing I would like to say is that integrating a CRRT machine into your ECMO circuit is off-label for the CRRT machine, or the manufacturers. It's off-label for their intended purpose of their technology. It's also off-label for ECMO. So it's a double off-label conundrum, but it is certainly clinically and in terms of managing patients a much better alternative than the risk of sticking that patient and having an access catheter that doesn't work very well, because that is the #1 cause of failure in the use of CRRT is, in fact, access problems. So keep that in mind. And when you plug it into your ECMO machine, you have really unlimited access. But again, I'll talk to you a little bit about how those pressures work with each other and what kind of things can interrupt the therapy, and how we sort of work around all of those things to make it work. So my diagram that you see up here is a basic CRRT machine. Now, in the CRRT dialysis world, unlike perfusion, red is your access, blue is your return. And a lot of people wonder why that is. Well, this is the reason why. If you take blood from a vein or an artery, doesn't matter, and you run it through a hemoconcentrator, which is the dialysis or hemofilter, or whatever you want to call it, dialysis filter, and concentrate or remove the plasma water, that blood becomes darker. And that's why it is red for access and blue for return. It's really brighter, darker, as opposed to red and blue in the classic sense that we view it when we go from venous access to arterial return. Okay, so in a basic CRRT machine, your access pressure, because again, you're hooked up to a catheter, right? Usually a Maherker or Quinton catheter. It's going to be 11 French more than likely. Maybe it's a 14 French, very rarely. That's a big catheter for a temporary dialysis catheter, but most of the ones that I see are 11 French. And that's going to be divided into 2 sections because it's a double lumen catheter, single catheter, double lumen. But your access pressure is going to be a negative number. It's going to be somewhere between -50 to -150. And that's going to depend on whether the access catheter is in the middle of the vessel with good flow, not having any obstructions on the vessel walls. It's going to depend on how fast this roller pump, this pump is turning. So the faster your flow, given the same size, and the viscosity of the blood and all those factors are going to influence the access pressure to be more negative. Once you get on the positive side, so this is the negative side of the pump head, this is the positive side of the pump head, right? You're going to have the resistance through the filter here and the resistance going back into the patient here, and all of that is going to be reflected back to the filter pressure. And your filter pressure, depending on flows and all of that kind of thing, are going to be somewhere about, of course it's a positive number, right? So we'll say about 100 to 200, somewhere in that range. So it can range depending again on your flow and a variety and how much of, and whether or not your return catheter is in a good spot. Usually these are double lumen. It shows it's separated, but usually it's a single catheter, right? Then if you look down here at your return pressure that you see right here, that is going to be less than your filter pressure, because your filter pressure is the resistance all the way from here all the way back to here, whereas now you're only measuring the resistance from here to here. So there's going to be a big difference in that, but it could also still be somewhere between positive 100 and positive 200. So basically, if you have a pressure here of 200, so I can go back here and just clear those markings. If you have a pressure here that is reading 200 and your filter is patent, you're likely going to have a pressure in this area here of about 140, 160, in that range. So you're going to have a pressure drop across the filter because the filter, the hollow fiber, is going to have a resistance itself through it. Now, this is a very important thing to think about, and that is, let me clear these markings. Very important thing to think about. Your effluent pressure can range from a positive 50 to a negative 150. However, the way this is actually intended to work is for this pressure here to always be positive, not negative. So in essence, you want the blood to be coming this direction, going this direction, and you want the pressure on the blood side to be higher than your pressure here on the effluent side, so that the plasma water is actually being pushed through the hollow fibers, the plasma water, into the pump. And the pump, instead of pulling the plasma water out of the blood, is actually intended to act as a dam to control how much volume, how much effluent, how much plasma water is being removed at any one time. So it's very important to understand that concept, that even though the technology will operate in a negative up to negative 150, depending on the machine you're using, millimeters of mercury, it's intended to operate in the positive. So positive 50, positive 100 would be fantastic as far as I'm concerned. And what you will see is if the pores of the hollow fibers that are in here become occluded with inflammatory mediators, proteins, whatever might be, that the ability for the plasma water to be forced through those pores is reduced, and therefore that's why it can operate in this negative area, because you want to pull that fluid out. Your filter is basically going to stop working, become clogged versus clotted. But that's another topic for another day, talking about CRRT. It can get a little bit overwhelming if you really look at all of this stuff, and we have limited time. So basically, let me go through all these numbers again. Your access pressure is going to be negative. Your filter pressure is going to be positive. You want your effluent pressure to be positive. You want your return pressure to be positive plus, I'm sorry, positive, my mistake. Positive, scratch that, positive minus. This will be positive plus. This is going to be higher than this. Yeah, that makes sense. Okay. So here you have a basic ECMO circuit, and it has a CRRT. I'm going to connect a CRRT machine to it. Let me see if that's, yes, that's here. So here in this particular diagram, we're only looking at the ECMO circuit. Your drainage cannula here, so this is your blood pump, your centrifugal blood pump or your peristaltic pump, it doesn't make any difference which. This is going to be a negative number, and it can range anywhere from negative 50 all the way to negative 200, depending on the flow, size of the cannula, resistance to flow, all of those kinds of things. So you have the blood coming down here. Much like in the CRRT circuit, anything past the pump is going to be positive. This is going to be, let's say, positive 100 to positive 250. And then, of course, you have resistance through the membrane here, so the pressure here is going to be somewhere about plus 100, plus 250, but it's going to be a number that is lower than here. So let's look at that a little more in detail. If your pressure here is negative 100, your pressure here is positive 250, your pressure here is going to likely be lower than this pressure because you have the added resistance through the membrane. So we'll say it's going to be positive 200. It could be positive 180. It could be a little bit lower than that. So normally speaking, you're going to have a delta P across any hollow fiber membrane oxygenator or microporous hollow fiber oxygenator, as the case may be. And then, of course, your return cannula will be your final point of resistance, and that pressure, of course, would be reflected all the way back to here. So it's that pressure plus the resistance here gives you this number here. Okay, so great. Now, if you look at a CRRT machine that has been already integrated into an ECMO circuit, they do it their way. This is a way to do it, Anil, but there are other ways to do it that I prefer, and I can maybe sort of articulate why. So here you have your drainage limb coming down to your centrifugal pump, and then you have your line going from the pump to your oxygenator. So from your pump to your oxygenator. This line right here is the line with the highest pressure in the entire circuit. So that is where your greatest amount of resistance is met, because again, you have the resistance from the return limb cannula all the way back through the oxygenator, the increased resistance there. So this line has your highest resistance in the circuit. This, of course, is negative, just like in the CRRT machine. So if you look at what they're doing, they're taking off of this very high pressure line with their access. Remember, red is access in a CRRT machine. And they're bringing it around, just follow it around, and they're coming in to the hemofilter, through the hemofilter, now down the blue line, which represents the darker blood, and it's coming in that line distal, but again, where the highest point of resistance in this circuit is. So if you remember what we talked about, the normal pressure that a CRRT machine expects to see in this arm, your access line, is a negative number, negative 50 to negative 150. But what it's going to see here is probably going to be, depending on flow and a variety of things, it's going to be positive about 200 to positive 250. So already you have a tremendous mismatch between your CRRT machine normal pressures that it expects and your ECMO circuit, where one is causing the other to look completely foreign, and it doesn't really make sense. And it's very hard sometimes to get these machines to accept, or accept would be a better way to say it, accept these very unusual, I kind of consider them in this, for the CRRT world, hostile pressures. Now, let's continue with that. Your blood then comes through and is returning to that same pressure line. Well, there is no CRRT machine that is designed, you're going through a Maherker catheter or a Quinton catheter, or temporary dialysis catheter. I need to just say temporary dialysis catheter, be easier. You're going through that, and your normal pressure on this return, if you remember we talked about, is going to be somewhere between positive 50 and positive 150. Maybe it can go up to positive 250 if you're really pushing it. But if you're already at a positive 250 in this line when it's expecting it to be just the resistance through a temporary dialysis catheter, now your return is seeing a very hostile environment. And to make these machines work in that kind of unusual circumstance, in my perspective, in my experience, has led to many, many alarms and a lot of frustration and a very inadequate therapy. So, but at the same time, in this regard, and this is very important. Oops, I'm so sorry. In this scenario that you see here, the good thing about it is that this pressure, this effluent pressure that's before this pump, is going to be very, very positive because of how high those pressures are. And you do want that. You don't want this pump, remember what I said, to be pulling the fluid across the hollow fibers in the hemofilter. You want the hemofilter to be pushing the plasma water across the hollow fibers, and for this pump to act more as a dam, controlling the amount of volume that ends up in your effluent bag, your ultrafiltrate waste container. So with that said, I'm going to show you how we do it. So I'm going to go over there to the simulator section, and we're going to go over our two systems, kind of show you what I have over there, talk about some different pressures. That's beautiful. And we'll go from there. But let me tell you what we're looking at this on the screen first. That might be very helpful. And I'll keep this up in case I need it again. So what you see here is the CRRT machine. This machine right here has above it, that you can't see in this picture, this screen. And I wish I had a full picture of that. Is there any way to, there's no way to do that, is there? I kind of want to see, let people see. Yeah, there you go. So you see in the very top there that screen. Okay, let's go ahead back down. So that's perfect. So this is just above this area here. So that's what you're looking at there. Here is our ECMO circuit that's hooked up to our simulator, but we're not going to be working on the ECMO simulator. We're only going to be focusing on this area that you see here where I integrate the CRRT machine. And of course, you have our ECMO flows that you see here, and we have our pressures. We have our return pressure, which is 133, and our access pressure minus negative 8990. But what I want you to notice is your access pressure, which is, I have it set up currently just in a saline bag and designed to sort of simulate what it would be in a temporary dialysis catheter. I'm not running any treatment. I'm only running the blood flow for the sake of this discussion. We may add that as we go forward because those things have impact. Both are closed circuits, two separate closed circuits integrated together, operating together but separately. And once you understand it, it's very easy to do and you completely get it. But if you don't think it through, your CRRT treatment, again, can be very ineffective and problematic. And that's what we're trying to avoid here. But what you see is an access pressure. We're flowing 250 cc's a minute. We can flow much, much more than that. When you're on the ECMO, you want to flow about 400 if you can. But for this demonstration, that's what it would be currently if it was in a temporary dialysis catheter. You see our access is negative 94, negative 88 in that range. Our filter pressure is 114. That's the pressure that you're seeing that's being measured coming up this line right here. So this is your access. This is the roller pump turning this direction, clockwise, going down, coming around, you can't see it, and this filter pressure is being measured by that pressure pod, and that's 114. Your return pressure, which is here, you notice it's lower than your filter pressure because, again, there's resistance in this filter, and that's reading a 61. That's being measured right here. So this is a deaeration chamber, and that's your pressure there. And you notice our effluent pressure is very nice at a positive 73. This is what you really would love to see on any of your CRRT treatments. It makes life very, very easy when it operates like this. We'll go over the CRRT machine just very quickly. You have your roller pump taking blood, again, access, going to return through the filter, out of the filter, coming into this deaeration chamber, going back to the patient this way. This is your effluent pressure pod. So the blood that's going to this is your ultrafiltrate that ends up coming through this pressure pod and ends up out going to the waste container that's over here. It's the yellow line. But we're not going to really be focusing too much on that. Our ECMO, we have our access line here in blue, which is what we're used to, going into our centrifugal pump. This, of course, is a negative pressure area. You don't want to open a stopcock down here inadvertently because it will suck air and deprime your cone. And in VV ECMO or VA ECMO, worse, it's very difficult to reprime a closed circuit like this without a reservoir. It then comes out on the positive side. This is that line I showed you that I discussed as being the place with the highest pressure in the ECMO circuit. And that's going to be the outlet of the centrifugal pump or roller pump coming down, coming into the oxygenator here. Then as you leave the oxygenator and come down this line going through the flow probe, there's a pressure monitoring line that you see right here, and that pressure is the return pressure of the ECMO circuit, which is being reflected by that 133. Okay, so I'm going to go over there and I'm going to talk. We're going to just focus on that part of all of this. I may come back here, but for right now, we'll go over there. Oh, I thought you were going to take it. I'll probably have to just walk this way. Okay, perfect. Okay, most excellent. Okay, welcome back. So I'm camera 2, and we can see, could you do me a favor? Can you turn that just a little so I can see it? Because it's hard for me to see behind that. Dude, that's perfect. Thank you very much. Okay, perfect. So here you see, and you'll be able to see my, my wand that comes in. We're looking at the, you saw that on the screen. You see our numbers right here. And you see here our flow. So you have our access line, which is the red. It's coming into the access pressure pod here, which is measuring the pressure coming from the temporary dialysis catheter in the patient before the roller pump. So negative side of the roller pump comes around, the blood goes through the filter pressure pod, which you're seeing right here, goes up into the the hemofilter, out of the hemofilter, now as you see blue, goes into the deaeration chamber, which is measuring now a pressure here, which is our return pressure, the blue line coming down and out, and then it's going to our simulated patient, which is a saline bag that you can't see. It's off screen. But a very basic system that you see here. And now this is the Gambro Prismaflex machine. I'm not necessarily the biggest fan it's Baxter Gambro now. I'm not the biggest fan of the company. I don't have any vested interest in any of these technologies that you see I have here. No stocks, no financial disclosures or anything like that. But in all frankness, this is an excellent widget, an excellent tool for delivering CRRT to your patients. So with that said, let's focus on what we were going to focus on here and keep moving forward. So can you make our ECMO, this part right here, a larger image, but keep the flow and the pressure, this part, still intact? Is that possible? To keep this and make that bigger or not? No, you'd have to set up for that. No, I didn't. You're right. Okay, that's all right. You know, I mean, it's like anything else. When you're actually doing it, you kind of come up with these ideas that you don't think about when you're thinking it through. But let's go ahead and make this one here, this section, much larger, because I just want to focus on this. Okay, so currently, what you saw was our pressures were about negative, do you remember what they were? Negative 89 and positive 133. And I'm measuring our negative pressure, our access pressure, right here in our access line. You can see it going up to a transducer that's right over here into our centrifugal pump. So we know this is going to be the negative side of the pump with a pressure currently of about minus 90. You then leave this pump and come through, and we're going to go ahead and measure the pressure here. I don't have it hooked up just yet, but as I told you, this is the highest pressure of the entire circuit between here, the outlet of the centrifugal cone, going into the oxygenator right here. You then leave the oxygenator, go through a flow probe on the way back to the patient right here, and here you can see we have a pressure line that is connected to the transducer, and that's where we're getting our 133 from. So go ahead and go back to the multi-screen. That's great. And hey, Magic, could you help me out and turn some dials? So what we're going to do is just watching the pressures of the ECMO circuit, we're going to increase the flow from 4 liters a minute to 4.5 liters per minute. So go ahead and do that. To 4.5, yeah, it's not going to be a big change. But watch the pressures. You see immediately the access pressure is going more negative, and the return pressure, of course, went more positive. You expect that to happen. So what I'm going to do now is I'm going to measure the pressure in this line that I talked about, which is the line with the highest pressure at the same flow, and compare it with the same transducer and compare it to what we see there. So that's good. 156 is you're perfect. Let's let it settle out. 156, that's perfect. Okay, so I'm going to come down here. I'm going to take my positive pressure line, turn it off. I'm going to add this to here and turn it on. And we'll see what that pressure is. And you see there what our pressure did, up to 263. So you have about an 80 millimeter pressure differential gradient, delta P we refer to it as, from the inlet of the oxygenator to the outlet of the oxygenator going back to the patient. So that's very important information for us to have. So if I wanted to hook the CRRT circuit up at 4.5 liters of flow into this line, and it wants to see a negative pressure, how am I going to create that negative pressure? So we'll go back to the other. So I just wanted to show you that difference. I think that's very important for all of us to remember how much different these pressures can in fact be. Okay, open this up. And we'll go back to about I think it was 153, 163, inside that range. So it should go back up. There we go, 156. 156, in fact, was the number. So that's perfect. So we see what that's doing. Now I want to do something which I think is interesting, is measure the pressure compared to those two, which was 250, right? 250, was it? Okay, somebody needs to write these numbers down for me. Somebody write these numbers down. I have a terrible memory. I'm getting old. Okay, I'm going to do this again. So we have, so put return 158. Put pre-oxygenator is going to be 263, 264. And now what I'm going to do is measure the pressure at the top of the oxygenator. Can you can't focus in on this area, can you? This where my finger is, in the bottom right screen. So at the top of the oxygenator, and every oxygenator has this, especially if you're using it for cardiopulmonary bypass, which is common, you have this line at the top of the oxygenator used for usually de-airing, recirculation. I'm going to measure the pressure here and compare it to those other pressures. Okay, now I have that on, and what do we get? So very interesting. It's reading 200, which is somewhere between what our pressure was here, and you can go ahead and zoom out, what our pressure was in the line going from the centrifugal pump, the highest pressure area, and the return. So it's between those two. Now I'm going to do something very interesting, and why I do this way. So what I want you to notice is I have a line that is a shunt line going from the top of the oxygenator back to the access side of the ECMO, the ECMO access line. If I open these lines completely, look at what happens to our return pressure. Even though that pressure coming out of here is high, the interaction of this access line, the negative pressure here, is being reflected back, and now this pressure in this port is actually lower than it's actually a negative number, which is very interesting. But that has everything to do with, now, you do, of course, create recirculation. When I open that up, so if I, so if I close this, look at what my pressures and my flows do. So flow is 4.7, 4.77. When I open it, the flow will go back down, or should go back down to 4.5 if I open the stopcock all the way. There it goes. Now, why is that? Well, I have my flow probe, of course, distal to where that shunt is. So anything going through this shunt is going to steal that blood flow from the power of the pump from this line, and it's going to go right back in. So you do have some inherent built-in recirculation when you do this. But at the end of the day, it's clinically irrelevant in my opinion, right? So that's why I do this way. Your access pressure is still quite low. And I have another question that I want to point out to you, and that is, do you think the pressure here, which is now negative 47, will be the same down here, or will this be even more negative, or will it be less negative? And I think that's a very interesting question that I wish to answer. So it was reading negative 47. I'm going to put it on the most distal stopcock. I'm going to turn everything back on the way it was. Yeah, that's okay. There you go. Everything is now open. Wide open. And it's negative 62. So the closer I get to this line, the more negative this number will become. All right, now I'm going to connect the CRRT circuit to the ECMO, and the way I am going to do it, and I'm going to show you on a drawing later as well, is I'm going to connect my access to this line here, and I'm going to connect my return here. Now remember, I'm going to probably flow 300, maybe 350 cc's, maybe 400, I don't know, we'll see, from the ECMO circuit into the circuit here. And that, of course, is going to result in some recirculation of my treated blood, because as I returned it here, some of that blood is going to come back in here through the system and eventually make its way back here. But if I'm flowing 350 cc's there and I'm flowing 4.5 liters here, that amount of recirculation is clinically insignificant. And based on, again, my experience, this makes the treatment more effective because it doesn't alarm, it doesn't stop, it doesn't get interrupted, and you can set it to where the machine sees very physiologic, the CRRT machine, physiologic numbers, making it work much, much, much better. So I accept that there is a level, albeit very small, of recirculation that will naturally occur. Okay, so for right now, I'm going to take this off. And again, what I said is you have to be very careful. You have to be very thoughtful, before you go pulling things off of these stopcocks, two things. One, you'll notice there's no stopcock on any of the connectors. They're always pigtails. You never want to put a stopcock on the connector. It'll break off, and there's nothing you can do about it. This is not going to break off. But the risk is if I turn this stopcock this way, take this off, it's going to suck full of air. It's a different scenario, but it can happen. Happens very quickly. In a sim lab like this, no problem. In a patient, big problem. So I don't think anyone but someone with a lot of experience should be doing this. Okay, so I'm going to go ahead and disconnect this now and put it back on my pressure line here. I'm going to open that up to read the pressure. And how are we looking? We're back to normal pressures again, right about where we were, negative 110 and positive 156, 157, somewhere in that range. So that all worked out really well. All right, so I'm going to now go over here and I'm going to pause the CRRT machine. And there's a variety of different ways you can do that. I could say I want to change bags, but I don't want to do that because if I do, then what's going to happen is it's going to keep the blood pump running. So I'm going to hit stop. But when you hit stop, you have to remember that if you had blood in this and you hit stop, static blood tends to clot a little easier, clogs things up a little bit, but we only have saline, so I'm going to go ahead and stop it. Generally speaking, when I do CRRT integrated into my ECMO circuit, I like to do it with a fresh filter, starting it off brand new. Generally speaking, I'm going to already have anticoagulation on board. If you're doing non-anticoagulation, you can still do regional anticoagulation of the CRRT machine, but you can also flow much more with this hooked up to this ECMO circuit and reduce your clotting because, again, that's flowing 4.5 liters. You can get away with a lot as far as low anticoagulation is concerned. Even at 500 cc's a minute, that's only a tenth of what you have over here, or just a little over a tenth, and it's going to have a much higher propensity to want to clot. So I'm going to go ahead and hit stop just for the moment and change this over. So you want to make sure, I don't know if you can see this or not. Can you see that? Yeah. Where is it going? No, there you go. So here are my lines. So they would, let's say be over there for the time. And I'll get this line here. And what I'm doing is clamping these lines to make sure that they don't entrain air when I disconnect them from our patient bag circuit that's up here. So normally I would take the red first because our red, as you remember, is our access. So the nurse or ECMO specialist or whomever would hand this to you, and of course it's telling you the blood flow stopped. I'm just going to silence the alarm for now. And you hook this to what is the most proximal port from the oxygenator. So I'm going to go ahead and connect this on here. Okay. And then I'm going to take the blue line, which is, if you remember now, my return, because they are different here. And I'm going to put this into the most distal stopcock in this 3 stopcock setup. And there's a reason why I have them set up with 3 and not just 2. You can do it with 2, but this gives me the ability to draw a lab if I want to. I could certainly put it here if I so desired, and or I can. Doesn't really make any difference. Which it depends on what you're trying to do. Sometimes you have to interrupt the flow just a little bit to get maybe a clean lab, but you can do that fairly easily. Okay, so I'm going to go ahead and open this, And I'm going to turn these stopcocks now the 180-degree point, if you can see that. Can you see that? So what I do is I turn them to the 180-degree point. So this is open this way, off to here. This would be off to there. This is now open. I turn it this way, and this maintains continuous flow through this loop simultaneously to flowing through the access and the return of the CRRT circuit. Okay, so let's go ahead back to the regular. There you go. That's beautiful, dude. I'm going to hit continue, resume, and I'm just going to go ahead and start this flowing at the exact same settings that we had before. And I'm going to go back over there so that I can point out some of these things. In Magic, I'm just going to need your help over here. So probably this is the best place for you to stand, is where I was. And I'll go over here. Yeah. Okay. Up. What's it say? Yes. So we'll go ahead and hit. You can go ahead and hit over continue. There you go. So let's let it go ahead and get started. Let me just wait here until it actually gets going. Good. Perfect. Okay, if it does it again, just hit continue. It may say override. Okay, adjust. And let me just fix this. 1 second. Override. And what I'm doing is trying to increase the... Okay. I need to adjust the chamber to go up. See how it's running real low? I don't know if the audience can see that or not, but I'm working on it. It's coming up. Good, okay. There, now we're in good shape. So what I did when I hooked it up to the ECMO circuit, what happened is what you see right here where I'm pointing to is the deaeration chamber. And because that pressure became so much more negative right here that you see, it sucked this level down much, much lower. If you get air in here, this is the air bubble detector, this is a brake. You get air in here, there's no fixing it. You have to just reset the whole thing up again. And I'm going to show you this, but this is an area that I want to be able to focus. Is there a way to focus in on this deaeration chamber at all? Right here. Let's see what you can do. Yeah, camera 7. So that's pretty. Oh, just make that big. Can you just make that big? Oh, that was good. And I mean, make it the full screen. Oh, that's good. Yeah, that shows it. You can see it. You can see it moving. Yeah, this is the deaeration chamber. So I'll give you an idea. So what I'm going to do is I'm going to pinch this line a little bit. And just if you can watch this, you should see it. Oh, that's going up. I'm sorry. Wrong one. I got to do it to this one. This one. You see it drop? Do you see it? See it pulling down? See it? There you go. Okay, good. All right. So, as I was explaining, all of these... That's all right. No worries. I got it. Oh, you go. There. That's perfect. Perfect. All of these pressures that you see here are going to interact based on what we do here, which you're going to see reflected when we do this here. So currently we're 124 access pressure and our return pressure is -17. I do not like those numbers. You don't want them to be like that. So Magic, what I want you to do is I want to make it worse, which is what it's going to do. Go to 5 liters and let's watch that access pressure and that effluent pressure of -5. Okay, so you see our access pressure got more negative, our effluent pressure became more negative, and of course our return pressure became more negative, as did our access pressure on the ECMO and our return here. So now, Magic, what I want you to do is I want you to go over and press this button that says adjust. Perfect. And I want you to click blood. And I want you to increase the rate that you see in the screen to 400. Just tap it. Tap, 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 tap. Perfect. And hit confirm all. Now let's watch and see what increasing the blood flow did for us. Look at the difference that it's already made. You have an access pressure now of 177. You have a filter pressure of 73, a return pressure of 10, but an effluent pressure which is now positive in the 27 range. So to show you how much the circuit will influence your CRRT machine, go down to 4.5 again, and let's watch and see what happens with these numbers. That's good. That's close enough. There you go. So we actually decreased our access. Of course, we decreased our access pressure on the circuit as well. We increased our effluent pressure and our return pressure. So if you think about it, currently, other than this pressure being a little on the low side, these are not that dissimilar to what you would ordinarily want to see. But I want to show you what happens when you close the recirculation line off and you're depending on the machine to overcome the pressure of the circuit without that recirculation line that I have in place. So I'm going to go over there and do this. It's easier for me to do it. So you can stay right there. So what I'm going to do is I'm going to, you don't have to move that. That's okay. I'm good. I'm gonna turn this stopcock off to this and turn this off to this so that this is just running out of here. This is just running this way, and see what it does. There you go. And immediately we got an alarm, and that alarm is going to say access extremely negative. Now it may reset itself, which it has. It has kind of come back. Check access, and you can see that now our access pressure is 46, our effluent is -41, and our return is 89. And if you can do this again for me, can you show this deaeration chamber right here, where my finger is? And look at how much lower. This was all the way up here to the top. You can actually see where it was, and look at how far it pulled it down. Well, if you leave this like this long enough, with that effluent pressure and that return pressure being negative, it will pull, because it's pulling out from here backwards. This will continue to fall, eventually getting to the very bottom, and then air again in your circuit. If I turn the flow of the ECMO up, this pressure will go down. If I occlude the access line, which I can do by simply putting some pressure on it here, you will immediately see this access pressure drop and you'll see that effluent pressure drop. It likely will alarm. Your return pressure is going to also drop because they are all going to be reflected back to this circuit. So I'm applying pressure. You see everything becoming more negative, and eventually it believes the set has disconnected. And the reason it believes that is your return pressure should be a positive number. So what I do is I have it going through the circuit completely with everything, as I said, wide open. I want that effluent pressure to be positive, and I want that return pressure to be a little more positive. So this is what I do. I put just a slight turn on this stopcock, which is my return line. And that is going to increase my return pressure, which will increase my effluent pressure. And so it's a very slight turn, not very much, but just a little bit of resistance. And now, if you look at the circuit, just by doing that, you have an access pressure that is negative. Again, that's what you expect it to be. That's what it would be at a temporary dialysis catheter. And you have a return pressure that is positive, what you would expect it to be with a dialysis catheter. And the reason why this machine keeps alarming is because we've changed the pressures so often, but you notice it doesn't really stop. Now, when you run therapies, whether it be pre-filter replacement or post-filter replacement, if you run dialysis with it, one, you shouldn't be using the machine to just run straight dialysis. Be that as it may, different topic for a different day. This device is made for CVVH. That's what it's for, is replacement fluid, either post-filter, which is preferred because you maximize clearance, or pre-filter if you're having anticoagulation issues or coagulation issues and you want to pre-dilute it before it comes through, but that decreases your clearance quite a bit, right? But I want you to watch these pressures as I add replacement post-filter. So I'll go to adjust, I'll go to replace, I'll turn the replacement on to, let's say 3 liters, which would be a great number for replacement, maybe even more depending on the weight of your patient. And we'll watch what happens to our pressures, and you'll see that it caused our pressures, our effluent pressure to go down a little bit, our return pressure to come down a little bit, and our access to change a little bit. And that's because now we are adding volume with yet another roller pump into this de-aeration chamber, which is being reflected this way, and all the way back through the circuit before you reach this roller pump. So it's going to have an effect on everything. But it's very easy to do. These numbers are tremendously physiologic. I'm very happy. Now, I would like that effluent pressure to be a little bit higher. My return pressure is 86. I can afford to add a little more resistance if I so desired. So that might have been a little bit too much, but we'll see. No, seemed to work out. So the return is maybe a little bit high, 217, but it's not bad. It's still positive. It's certainly not as high as what we have in the ECMO circuit or any worse. Like this? That good? Oh, I'm sorry. Okay. Our access pressure is positive. It should be negative, but this doesn't hurt anything. Our filter pressure is 270. That's a little high, but that doesn't hurt anything. That's resistance. That's not because the filter is being clogged. Our effluent pressure is 125, which is great. It's very positive. This effluent pump is acting as a dam, and our return pressure is 220. Again, maybe a little bit high, but not anything bad. This is going to give you hours and hours and hours, days, because the filters are good for 72 hours. This will give you a very long filter life, uninterrupted flow, and it's all going to work well. Now, caveat to that is if your patient is having volume problems and you're having to fluid resuscitate and do all of those kinds of things, might not be a good idea to have this there then, because if you have continuous interruption and these pressures change a lot, which I'll just demonstrate, you're going to get alarms. Alarms are a big hassle with these devices. They're very, very useful tools, but have pretty high sensitivity when it comes to varying pressures and flows. So I'll give you an example. I'll just act as if we were having chatter. And you see, you know, just by doing that enough times, we finally got return pressure dropping. So it's very sensitive and it sees all of those kinds of things. Okay. All right, so with all of that said, and of course there's limitations, Magic, if you want to just do this, if you're going to be messing around with it and going up on the flow and down on the flow, so the flow on the ECMO, and you can just vacillate it, let's say down to, take it down to 3 liters, and you'll immediately see these numbers all change. Sometimes you will or won't get an alarm, but you see these numbers change. If these numbers change, these numbers are going to change. And of course you change this number and everything else is going to go along with it. So just ramp it up to 5.5 liters. And what you'll learn, you'll see everything kind of happen. And of course, remember I have resistance, but you're getting a check access alarm. It's not stopping, it's just telling you to check it. So go ahead and hit continue or override, whatever that says right there. There you go. And you can see it reset all of those pressures, but they're a little more unusual. So when you make changes to your flow or to anything else, you might also have to change your stopcock down here, how much occlusion or resistance you're putting on the circuit. Maybe you have to decrease the flow over here in the CRRT machine just a little bit, or maybe you just have to turn this flow down just a little bit, or just do everything gently until you get it in sync in the way you want it to be. And this is how I do it. So let's go ahead and go to my slides, and I just want to show this real quick. And so what I did in this case was I had the top of the oxygenator was our access, and this is what's going up to here. And the return is, actually, let me redo that, my mistake. We have a line that goes from here to here, and I have access here and return here. This is going up to here, and this is coming down from here. That's the way our system works. And I use occlusion in this area here, a little stopcock turn, and there's a stopcock here for sampling, in order to create the level of resistance I need so that my effluent pressure here is positive. This, I have no issue at all with my access being positive, even though it's designed to be negative, but it will work in positive and has no ill effect whatsoever. And I want this to be positive, these pressures to be positive as well. That's how I do it. And I can send you some of this, Anil, as a drawing, but I hope this explanation helped a little bit in understanding why I do it the way I do it. Now, one thing we didn't do, how much time do I have? Do I have time or did I run out? I'm over? Okay. Well, I was going to demonstrate, can we take 5 minutes? Just 5 minutes. Okay, I'm just going to take 5 extra minutes, and I'm going to hook the CRRT machine up to the circuit, only I'm going to do it the way they've done it here just to see what it would do. I would never do it that way, but I'm curious to see what it would do. Okay. I believe I can do it. I can hook one up to it. I can't hook both. So let me pause this and turn this, and my access, no, I need to leave that open. My access, so I'm just going to hook my access up to that and see, but see, they have the return up to it as well. So I'm just going to hook the return up to it. I think that makes more sense. And that's a small line. Yeah, I can't really do it and show it. I probably should have planned that out better. I'm trying to do it on the fly. I don't think that's really going to work. So I'm going to abandon that idea. But for those of you listening, Anil, I do not recommend doing it this way, the way it is in this diagram, because I think this pressure and this pressure are both going to just be too high in order to really operate the system with good flows and have pressures that you're going to be able to work with. So my recommendation is to do it the way I showed you, with a line coming out of the oxygenator, making a loop going down back into your venous access line of the ECMO. Actually, that's not even correct. It goes from here to here. So my mistake there. Flow going there, flow going this way. I have this connected to the access like this, and we have the return coming to the coming this way, going back in here, and then back into the pump. Again, there's some recirculation there, but again, this is 5 liters per minute. This is at the very best 500, but probably 400 mLs per minute going to the CRRT machine. So your recirculation, that actually gets captured back, is going to be a fraction of that fraction. So really clinically insignificant. I hope that answered your questions. I'm sorry I ran a little bit over. If you have any questions about this, please don't hesitate to reach out to me. You know you can do that at contact@perfusioneducation.com or info@mediweb.us, or my email address that most of you probably know. But I think you can find it all on our website. David might be able to throw it up, I think, at the end of the video. Yeah, he can do it right now. He can throw the little scroll bar. You can do Facebook Messenger. You can do Twitter. You can do LinkedIn. You can do, but that's probably the best way to reach out to us right there. There's all kinds of ways to do it. Thank you very much. I appreciate your time today, and I apologize for what happened Friday. This was our makeup session. I let the board know so everybody's good to go if they're looking for this for CEUs and you watched today. Thank you for your time, and we'll look forward to seeing you in a couple of weeks. It's next week. We'll look forward to seeing you the 13th and 14th of next week. All right, sounds good. Thank you all. Bye-bye.